Hello everyone, my name is Hamidreza Arkian. I'm a PhD student in the University of Rennes and I'm going to present our work that its title is an experiment-driven performance model of stream processing operators in fog computing environments. Well, in recent years, thanks to the development and deployment of Internet of Things, we started to use more and more internet-connected devices in our everyday life. IoT is tightly coupled with the cloud computing. In fact, the growth of IoT and the rapid development of the related technologies and application scenarios have led to the production of a huge amount of data that need to be stored and need to be processed. And here, cloud computing is the computing paradigm that could be really helpful in processing and storing this huge amount of data. And these two main components are connected to each other with the network. We know that a large part of data that is generated under emerging applications in the IoT domain is generated as a continuous streams of data. And stream processing technology was created to implement a data analytics task over these unbounded streams of data. And several stream processing engines have been developed, and the most famous ones are Apache Storm, Apache Spark, and also Apache Flink. We have used the Apache Flink in our experiments. Okay, but there is a challenge here. As I told you, the stream of data that is continuously generating from the IoT devices is with a high rate, has a high rate, and in other side, the applications, the stream processing applications are mostly latency sensitive or throughput sensitive, and in the middle we have a bottleneck, the network. The network here is the bottleneck because the network infrastructure has not been designed to support this huge amount of devices, to support this huge amount of high rate stream of data. But here is where the geo-distributed geo-distributed computing paradigm could be helpful, like fog computing. We distribute some microservers somewhere close to the edge of network, and then they will help in computation, in processing, and also in service providing for the edge devices. Well, stream processing engines and stream processing systems naturally designed for centralized, powerful centralized clusters, but based on their execution model, they can be mapped to the distributed environments also. Let me describe it more. A distributed data stream processing system expresses an application as a workflow of multiple data transformations that we call these transformations as operators, and execute the workflow over the input data stream. And also about the execution model, many of stream processing engines have developed different prioritization mechanisms. For example, they have, for example, pipelining, replication, and distribution, and so on. Okay, now let's assume that we have developed and deployed a fog computing infrastructure on a smart city. Now, if we want to map that execution model to this environment, to this geo-distributed environment, we can see that possibly every operator will replicate and will be distributed in different places, and every instance has heterogeneous network. So now there is a new challenge. Any configuration decision, like, I don't know, replication factor or replacement of the operators, any configuration decision can have a significant impact on the overall quality of service, on the performance of the whole system. So for this reason, we tried to propose an experiment-driven predictive performance model for stream processing systems in fog environments. Now, before talking about the model, let me first describe our experimental environment. We worked with a 32-core server, and we run 16 fog nodes in that server, and we also used some emulated network latencies between each pair of the fog nodes, and also we run Apache Flink on top of them. And for the application, we use 100,000 tuple 2 records as our input stream, and also we call inside of the operators, we call Fibonacci function to tune the computation complexity of the operators. And as the performance metric, we use processing time. And processing time means the time that one specific operator needs to process 100,000 records. Well, we focused on one operator at a time, and the operator is connected to a source and a sink, but the operator can be replicated, and every replica also can have some network latency, and that curve is the result that we get. It is clear that when we increase the number of replicas, the processing capacity will increase, and consequently the processing time will decrease. But you can see that there is a fluctuation in the curve, and this fluctuation comes from the network latencies. It means when we add a new replica, it has its own network latency, and this network latency has an influence on the overall performance. Okay, so we are going to model that situation based on those parameters like the replication, network latencies, and so on. But in first steps, we focus on the most important parameter, and based on the as you can see in this graph, it seems that the most important parameters is the number of replicas, and the number of replica, and the processing time follows the number of replicas, and it means the resulting curve is 1 over n curve, and it means when we increase the number of replicas to n, the processing time proportionally decrease by n. And if you want to get to use this model, you need to get the value of alpha, and alpha here is the computation capacity of a single node. And for having the value of alpha, you need to have 1 point on the curve or have 1 measurements, and then you can predict rest of the points. You can see the results in the graph. The difference between the actual values and the predicted values is a lot. The model is not very good, but we can say that it's not totally terrible. But wait, next model would be better. In next steps, we try to also add network latencies. Well, it's clear that the more time that you spend in the network, the slower system execution that's going to run. But we found that among different network latencies from the different replicas, the most important one is the greatest one, and this is the one that determine the performance of the system. So we added the maximum network delay to our model. We also added the gamma parameter as the impact of network delays to the overall performance. Now, based on the two measurements or 2 points, we can get the values of alpha and gamma. And if we predict the other points, you can see the difference between the predicted curve and the actual values. It's really perfect. In some parts the two curves are not identical. But can we even do it better? Yes, we can improve the model accuracy. We also found that there is a polarization inefficiency when we increase the number of replicas, when we increase the replication factor. So we added beta parameter as the polarization inefficiency of the stream processing engine, and in our case of Flink. Now we have a complete model, and based on the 3 points or 3 measurements, we can get the values of alpha, beta, and gamma. And you can see the resulting curves. The predicted curves, the curves of predicted values are much close to the actual values. Well, I told you that for using the complete model, we need 3 measurements. But in many real situations, we only have the first measurements. But we saw that even with the first measurements, we can use a version of model. The prediction result is not accurate enough, but it's good. Even it's still good. But we can see that as soon as we have the second measurements, the prediction accuracy improves much better to much better points. And when we increase the number of measurements to, for example, to 4, the error of the predictions are around 2% of the actual values. 2% error. Okay, so far we just focused on one operator, but in many cases the workflow has multiple operator, and can we use that model for modeling an entire workflow? For example, here we have a workflow with 3 operators: map operator, keyby, and radius. Every of them has their own replication, network latency, and of course the throughput. We know that the throughput of the overall workflow is limited by the throughput, by the slowest one, by the lowest throughput. And it means we can say that the processing time of the workflow is the maximum processing time between the operators. And based on our experiments, you can see that the processing time of workflow is somehow close to in this case with map operator that has the greatest processing time. Okay, now we have multiple operators, and we saw that if we want to model every operator, we need 3 measurements to use the complete model, to calibrate use the calibrated model. And if we have multiple operator, it means we have a lot of measurements. We need a lot of measurements. But can we reduce the number of measurements? Can we reuse the parameters from one model to another model? The answer is yes. About the alpha, we can't really reuse it, because alpha is specific to a computation complexity of one operator in one application. But about the beta and gamma, they are more independent. We can reuse them from one model to another model. And you can see the result in the graph. For example, here the blue bars are for uncalibrated model with only 1 measurements. And for example, the orange bars are when we reuse beta and gamma from one model to another model. And you can see the difference. The result is not perfect, but it's good enough. Much better than uncalibrated model. So, yes, we first talked about the challenge in geo-distributed environments, the heterogeneous network characteristic challenge, and we talked that it makes difficult to understand the performance, the overall performance of stream processing engines and stream processing applications in this environment. We tried to propose a predictive performance model that is backed by the experimental measurements, and we also finally showed that the prediction accuracy of our model is around 2% of the actual values, and it's perfect. Okay, thank you very much for your time. Bye.